second part, we will continue computing limits as x goes to plus or minus infinity. Then we will start talking about asymptotes of a given graph. So let's look at these two questions now. We want to compute the limit as x goes to infinity. Again, we have a similar situation on the behavior of this function. It behaves like infinity over infinity, obviously. As you insert infinity for numerator and denominator, they are both too big. Now, we need to invent something to get rid of that indeterminate form. And we will do, again, decomposing polynomials. So x squared, you can take it out, 1 over 1 plus x squared, square root like this, and do the same for the denominator like that. Now, we can evaluate square root on this part, right? You can take it out from the square root. At this point, I can put a recall here. So how do you evaluate this? Square root of x squared. How do you evaluate it? Any questions? Okay, so how do you evaluate that? Obviously, you need to evaluate it inside the absolute sign. So it is not just x, I warn you, you have to put this absolute sign too. So let's use it in our computation. So I will take this x squared out like that. Then it is 1 over 1 plus x squared inside the square root and x1 plus 1 over x. Now, we need to evaluate absolute sign. Look at here. X goes to infinity tells you something about the sign of x. So is x positive or negative? Tell me, please. X is around infinity. So x is obviously positive.
Positive.
Exactly. That's why we can evaluate this absolute sign as exactly it is without putting an extra minus sign in front of it. It is just x. Then everything resolves. As x goes to infinity, we have what? We have x, 1 plus x squared inside the square root, and x again, 1 plus 1 over x. You see, we obtain a simplification like that. As x goes to infinity, 1 over infinite is 0, 1 over infinite is 0 again. So we end up with just these coefficients. So the result is square root 1 coming from here, which is 1. Okay? Now let's try to understand the same computation as x goes to not plus infinity, but minus infinity. Okay, first of all, the behavior of this function. Numerator is infinite, denominator is minus infinite. Again, this is an indeterminate form. That's why we need to invent some simplification. Everything is the same till here. So I directly take this part from the above computation. Okay, so this time, tell me, by the way, let me put minus infinity because it is the question. X goes to minus infinity, then what is the sign of x? X is around minus infinity, so it's negative. That's why I will evaluate this absolute sign as minus x this time, because x is negative. By putting an extra negative sign in front of it, I make it positive. Okay, so I have this x like that. Again, simplify, send these parts to 0 as x goes to minus infinity. So the result is like that with an extra minus sign coming from here. So the result is minus 1 in this case. Okay? Any questions? So let me move on then. Now, we will search for the limits for the indeterminate form of infinity over infinity. This is also an indeterminate form. Be careful about that. Okay, this is not 0. Be careful. This is an indeterminate form. So let me show you an example on that. 80 9, for example. So let's deal with that. Limit as x goes to minus infinity, 2x for x squared plus 3x minus 2, okay? Let's try to understand the behavior of it. As x goes to minus infinity, 2x is minus infinity, obviously, and this part, just look at the dominating term for x squared, it gets plus infinity. So what is this? This is infinity minus infinity. Be careful, it is not 0, okay? If you say that this is 0, you are wrong. This is an indeterminate form. Indeterminate form, and you need to work harder to get rid of this indeterminate form to obtain your result. What can we do for this question? Okay, we will use the idea of multiplying and dividing by the conjugate of this expression. We used it last week, if you remember. So the conjugate of this expression is this very same thing, except this sign in the middle. It is plus, and I put minus for its conjugate, okay? I multiply by it, and not to change the problem, I need to divide by it too. Okay, then what happens? Then we have, okay. So this is now in the form of a plus b, a minus b, so that I can multiply them quickly as a square minus b square, right? Let's do that. As x goes to minus infinity, a square is for x square minus, this is b square. So I will write minus this thing without square root because I am squaring it. So minus 4x square minus 3x plus 2. As it is a square minus b square, I multiply everything with minus 1. Okay? And then at the denominator, I obviously have this one. Don't forget to write that. Like this. Okay, you see we start having some simplifications already. And then if you insert x goes to minus infinity, numerator is minus times minus plus infinite. Denominator is again something like infinity minus infinity. So situation is still complicated. That's why we need to now take highest degree term parentheses for this question. Okay. I will write the denominator as like that. I decompose it like this. I take x out. Sorry, this is 2. Is that okay if I write the denominator like that? And then at the denominator, please look at this part. Highest degree term is x squared, then I can write it like 3 over x minus 2 over x squared. And then inside the square root, I have an x squared as a multiple, as a product. Then I want to take it out. How can I take it out? I need to evaluate it as absolute sign. Be careful. We just learned that if you want to take squares or even degree terms out from square root, you need to use absolute sign always. The absolute sign of x, then I have this inside the square root. Okay, next. You need to evaluate now this absolute sign thing. Look at x values. X is around minus infinity, showing you that x is negative. That's why you need to evaluate the absolute sign with a minus in front of it so that you have minus minus plus here. And let me rewrite the expression in a more simpler form. Minus 3 plus 2 over x divided by what you have, x at 2x plus x times something. So I can take x out again, like that. So that's what I have. Then sorry, I made a mistake here. I shouldn't have written x. I already take it out, like this. And then you start simplifying these two. Then as x goes to minus infinity, what is 2 over minus infinity? Tell me, what is 2 over minus infinity? It is obviously 0, right? You divide 2 by a very, very huge negative number. 3 over minus infinite, 0. 2 over infinite, 0. That's why now we see the result. After all those simplifications, minus 3 is what we have at the denominator. And at the denominator, we have just this. So the result is minus 3 over 4. Okay? Any questions about this solution? This solution, in this problem, we have infinity minus infinity, which is an indeterminate form. That's why we need to invent something. We need to do something to invent some simplifications. That's why I multiplied and divide by the conjugate of this expression. After multiplying that, we start having simplifications. At some point, we obtained x squared in the square root as a product, and then I can take it out inside the absolute sign. I evaluated the absolute sign by deciding the sign of x, it is negative. That's why I put minus x here. And then everything resolved. Any questions about that? Okay, I move on. Here, I put a very big recall for you because about this point, I get lots of questions from students. According to my experience, I decided to put this recall here. This recall is about this limit, okay? What happens to the function f 1 over x around 0? If you approach from right, for example, the more closer you get to 0 from right, the bigger values you obtain, and you can get as big as you want by taking x more closer to 0 from right? So you see that as x goes to 0 from right, so this limit, look at the values. The values get as big as you want, and this kind of behavior is described as putting this limit equals to infinity, okay? Since we are putting equality sign here, students may get confused sometimes because by putting equal to something, putting equal to infinity doesn't mean that limit exists. Here, limit still doesn't exist, okay? Limit still does not exist. Also, from the other side, also look at from left, for example, x goes to 0 from left, x goes to 0 from left 1 over x. This time, look at the graph. From left, you can make the values as small as you want as you get more closer to 0. You can get arbitrarily negatively small numbers. So this kind of behavior is described as by putting minus infinity to this limit, okay? So this is plus infinite, this is minus infinite. Your values diverge to minus infinity, here they diverge to plus infinity. And by putting equal sign here doesn't mean that limit exists. We still say that limit does not exist. Limit still does not exist, but by just putting equal minus infinity or equals plus infinity, we are just giving an extra information about the behavior of our function. It diverges to plus infinity, it diverges to minus infinity. We are just giving an extra information here, okay? So let's read this warning together once at least. We are not saying that limit exists here, nor we are saying that there is a real number infinity. No, we are just describing the behavior of this function as x goes to 0 from left or right, that it goes to plus infinity from right and it diverges to minus infinity from left. Still, limit does not exist, okay? Is that part clear? I think I made myself clear on this part so that I can move on. Okay, next. Let's try to analyze a similar kind of behavior in this example. This is a very basic example, but it is important on understanding limits as infinities. Okay, so limit of this function as x goes to from right. Okay, this one. X minus 2, x plus 2. What do you think what this limit is? 2 is here and we are approaching from right, meaning that we are inserting 2.00001 kind of number. And if you subtract 2 from this kind of numbers, you obtain 0.0001 kind of values, so that you are what we are doing here, you are dividing 1 like something 0. So it is plus infinite because this is getting 0 from the positive side. And the other one, limit x minus 2, x plus 2 as x goes to 0, this time from left. Okay, so what is happening here from left? You're approaching from this direction, so you insert 1.999, this kind of numbers. So this part, if you subtract 2 from this number, you obtain minus 0.1 kind of things. So you see that denominator gets closer to 0 from the negative side. Okay, you are dividing 1 to 0, but the denominator gets towards 0 from negative side. That's why this is minus infinite. Okay? Don't forget to read these questions like that. Okay, I move on if no questions. Now, during the last half an hour of this session, I will talk about asymptotes of the graphs. Okay, so as I explained in a very detailed way in my recorded lecture video, there are 3 kinds of asymptotes: horizontal asymptote, vertical asymptote, and oblique or slant asymptote. Horizontal asymptote means what? Look at this graph and try to understand its behavior on this part. Let's say this point is 1, and let's look at the limits here of this blue graph function, limit of f of x as x goes to infinity. So for very large values of x, your graph gets closer and closer to which value? What is this limit? This value is 1. Yes, this limit is 1. If this is the case where the limit as x goes to plus or minus infinity is a finite number, then you call this line, this horizontal line, which is this one, as the horizontal asymptote, okay? This is y equals 1 line. I will skip this part a bit quick because you already watched that part in the recorded video. I'm just summarizing it. In this graph, for example, okay, this part and this part. Okay, this part is related to as x goes to infinity. Okay, let's again say this is 1 and this is minus 1. This limit is 1. On the other side, when x goes to minus infinity, the values of this red graph are getting really close to minus 1 this time, right? So this is the first example. This is the second example. This example shows that a graph may have at most 2 horizontal asymptotes, okay? Like this one here, y equals 1 line, which is this one, and y equals minus 1 line coming from this limit. These 2 horizontal lines are the horizontal asymptotes of this graph, as they are indicated here as the dashed lines, okay? Horizontal asymptotes for the second case. And the third case shows you a graph may intersect its horizontal asymptote several times. Okay, let's put it here. A graph may intersect its horizontal asymptote several times. This may happen. You see this dashed line here is the horizontal asymptote. As you can see that the red graph approaches to this dashed line, and your graph intersects with the horizontal asymptote. This is the horizontal asymptote of it several times. What about the vertical asymptote? This time, you will look at this behavior. Let's say this point is 1, from left, from right. If you look at the limit of this function as x goes to 1 from left, 1 from right, or as x goes to 1 from left, what do you see? From right, your graph takes very huge values. So this limit is infinite. From left, again, similar behavior, very huge values, infinite. If this happens, if x goes to some finite number, if the limit is plus or minus infinite, sometimes it will be minus infinite, as in this case, then you call this vertical line you call x equals 1. This is a vertical line, the one here, as the vertical asymptote. Okay, let's look at the second example. Here, your values gets minus infinity from right, and from left, your function approaches to plus infinity. That's why, again, let's say this is the point 1. X equals 1, this vertical line is a vertical asymptote. And sometimes it may happen that, in the third example, it may happen that only from one direction. In this case, only from right, your function may have plus or minus infinite values. On the other direction, everything may be okay. No problem, there are no infinities on the left, but on the right, the limit of this function from right is minus infinite, as you can see. So you still call this vertical line, x equals 1 line, as a vertical asymptote. This may also happen. And finally, oblique asymptote is what? Oblique asymptote is, in fact, the generalization of horizontal asymptotes. You see, this is a horizontal line. In the oblique case, we let this horizontal line to be any line. It doesn't need to be horizontal anymore. Now it is in this form, y equals ax plus b. Any line like that, any general line. And as you see over here, your function, the red graph, approaches to our oblique asymptote y equals ax plus b line as x goes to infinity. Is this correct? You see, the red part gets really close to this green line as x goes to infinity. So they behave like the same around infinity. For such cases, you call this line as the oblique asymptote. Okay, this is a summary of 3 types of asymptotes very quickly. Now, let me show you formal definitions and some particular examples. Okay, horizontal asymptote, as we discussed, you will look at the limits as x goes to plus or minus infinity. And if you obtain some finite value for the limit, then you call that horizontal line y equals b line. This is a horizontal line as the horizontal asymptote. Here is the example of it. This graph, okay, let's investigate the behavior around infinity and minus infinity. Here, what happens? Limit of this function as x goes to infinity is what? The values are getting closer to which value? This is 3. They get closer to 3. That's why y equals 3, this horizontal line is a horizontal asymptote as it is indicated here. And also on the other side, limit of your function as x goes to minus infinity is 3. So this dashed y equals 3 horizontal line is a horizontal asymptote for this graph. Does this graph has an vertical asymptote? You see, it has also vertical asymptotes. Investigate the behavior around 1. So what happens here to your function? As x goes to 1 from right, this is the point. You see, the values are getting plus infinite. Also, as x goes to 1 from left, you see that x goes to 1 from left, you see that your function gets very small values like minus infinity. If this is the case, then you call this vertical line x equals 1 is a vertical line as you call it as the vertical asymptote, okay? This line here, x equals 1, is the vertical asymptote for your graph. Also, similar behaviors you can detect for x equals minus 5. It is also a vertical asymptote for this graph. Is that okay? So after this example, you can understand this formal definition of a vertical asymptote better. As x goes to some finite number, we used 1 in this particular example, from left, from right. If the limit becomes plus or minus infinity, then you call this vertical line x equals a line as the vertical asymptote. Okay, x equals a is a vertical asymptote if one of these cases happen. If the limit around that number from right, from left, if the limit appears to be plus or minus infinity, you call this vertical line as a vertical asymptote. Here is an example of it. 1 over x is our famous function whose graph is like that. Around 0, what happens to this graph? You see the behavior of it, right? Around 0, let's investigate the behavior of this function. X goes to 0 from right. Limit of f of x, x goes to 0 from left. On the right, it gets very big values, infinite. On the left, it gets very small, huge values, minus infinite. This shows that this line is a vertical asymptote for this graph, as it is indicated here. Also, there is a horizontal asymptote for this graph too. Look at the behavior of your function around plus or minus infinity. This time, we compute the limit as x goes to plus infinity or minus infinity. So 1 over, look at the behavior, or you can just insert infinity to here. 1 over infinite is 0. Again, 1 over minus infinite is 0. That's why y equals 0 is the vertical horizontal asymptote for this graph. Horizontal asymptote. Okay, any questions? So far, so good. Let's move on if no questions. Now we will talk about oblique asymptote a bit. Here is the formal definition for oblique asymptote. It may seem a bit complicated at the first sight, but let me try to make it easier for you. I will put a remark about oblique asymptote to understand that formal definition. Remark, okay. Let me draw a graph and then I will insert a function and an oblique asymptote there. Okay, let's say this is our this will serve as our oblique asymptote. Our graph, let's draw a graph like that. Let me try it again. Okay, this is nicer. So let's look at the behavior of this function around this line. I mean, over here and over here. As you can see, our function f of x approaches to this green line, y equals ax plus b, as x goes to infinity. Is this correct? What do you think? Is this correct? Does the values of your function approaches to the value of line as x goes to infinity? Yeah, you can see it from the graph. They get closer and closer. Also over here, what happens? The same situation happens. F of x approaches as x goes to minus infinity to this green line. Y equals ax plus b. So if this is the situation, then or if your function gets closer and closer to some general line like that, if they behave like the same as x goes to plus or minus infinity, then you call this line as the oblique asymptote. Okay, oblique asymptote. This is the informal explanation of it. Now, I will show you the formal explanation again, and you will understand it this time. Before that, let me repeat my sentence. Around minus infinity or plus infinity, the graph, the function, and the oblique asymptote behaves like the same, right? It is kind of like there is no difference between, like there is no difference between f of x and the line y of x, right? They behave like the same. That's why your course book defines oblique asymptote like this. This is the function, and this is the oblique asymptote line, y equals ax plus b. And as x goes to minus or plus infinity, they behave like the same, okay? They behave like the same. That's why if you take the difference, you obtain 0 around plus or minus infinity. They behave like the same. Okay, that's why the difference of them around plus or minus infinity are nothing, just zero, because they behave like the same. This is the formal definition of oblique asymptote. Let me show you examples on the graphs. Look at the behavior of the given function x squared over x minus 1. Over here and over here. Limit of this function as x goes to infinity. Maybe I should have written it like this. F of x goes to this line. This line is given as x plus 1. This f of x approaches to this line as x goes to infinity, and also your function again behaves like that green line. It approaches to this green line, x plus 1, as x goes to minus infinity too. That's why, since we see this behavior over here and over here, we can call now this line as the oblique asymptote. I mean, from the graph, it is really easy to detect oblique asymptote. This time, our oblique asymptote is y equals x, for example, in this case. This graph, turn back to this graph again, also has a vertical asymptote at 1, right? Why? Because from right, it gets plus infinity, and from left, the values are getting closer to minus infinity. That's why x equals 1 is a vertical asymptote as it is indicated here. Okay, any questions now how you can read oblique asymptotes from the graph? It is not that difficult. You just see that there is a line towards which your graph is approaching around plus or minus infinity. But let me address a question for you. What if you don't see the graph in front of you, but still you want to find the oblique asymptote of this function, for example? Can you do that? Okay, there is a way to handle this question. Let me explain. Let me say, what if we don't know the graph and still we want to compute the asymptotes of f of x equals, let's choose this function, x squared over x minus 1. Can we handle this question? The answer is yes. And here is the explanation. Let me put the answer. If your function is in this form, px over qx, this is an answer in general. You will look at the degrees. To detect the oblique asymptote, you will look at the degrees, okay? Degree of the polynomial in the denominator, if degree of px is 1 more than the degree of qx, which is the case here, degree for the denominator is 2, degree for the denominator is 1. And this situation holds, right? Degree of numerator is 1 more than the degree of the denominator, then there is oblique asymptote. There is oblique asymptote. This is the very quick way of detecting if there is an oblique asymptote or not without looking at the graph. Okay, then how, okay, now we are sure that there is an oblique asymptote, but how we can find the equation of it, how we can find y equals x plus 1 line as the oblique asymptote. And the answer for that, how to find it? Okay, let's write the next question. How to find that? And the answer is use polynomial division. What do I mean? You will divide these two polynomials like that by using polynomial division algorithm. Okay. You will complete this division. Let's say you obtain something like this here, and you obtain a remainder here. And then what you see here at this part will be your oblique asymptote, okay? This will be the oblique asymptote for you. And as you all know from high school, this rational function can be rewritten by looking at the details in this polynomial division as ax plus b plus remainder over qx, right? Okay, this is how you can rewrite your function, and this part will be your oblique asymptote line. Okay, this is the answer for that. Now we can apply all of these things for our exercise. Okay, we were dealing with this function, x square of x minus 1. Now I am checking the degrees. Degree is 2, degree is 1. Let me also write. Here, degree for denominator is 2, degree for the denominator is 1. And just like I indicated here, degree of denominator is 1 more than the degree of the denominator. So there is oblique asymptote. How to find it? I will perform this polynomial division quickly. X minus 1, I will multiply by x, subtract, and then I have x. I need to multiply plus 1 by plus 1, like this, subtract. Okay, the division algorithm is over because I obtained this remainder. Then what you see here is the equation of your oblique asymptote. And let me also rewrite this function by looking at the result of this polynomial division. Okay, so I can write it as this part plus remainder over this part. Okay, and this is the oblique asymptote part. Yeah, like that. Y equals x plus 1 is the oblique asymptote of this function. And finally, I also want to mention something else. What about the other asymptotes of this function? Okay, oblique asymptote is handled like that. Is there any other kind of asymptote for this function? Look at the denominator. So there is a vertical asymptote of it. You know, we detect it by looking at the graph, but if we don't know the graph, but we also need to find the vertical asymptote. For the vertical asymptote part, you will look at the denominator of your function, okay? Here is the denominator. You will search for the zeros of it to detect vertical asymptotes. Search for the zeros of x minus 1. What do I mean here? The denominator is 0 for x equals 1. This is the candidate for the vertical asymptote. Candidate for vertical asymptote. To verify that it is in fact a vertical asymptote, you need to look at the behavior of your function around this point, from left and from right. Okay? So let me also write the other one-sided limit here. X goes to 1 from left, okay? Then from right, if you insert 1 here, you get 0 at the denominator and it gets to 0 from the positive direction. That's why it is plus infinite. If you insert some number from left as x approaches the 1, okay, you are getting 0 again from the negative direction. This is minus infinity. So this verifies that x equals 1 is in fact a vertical asymptote. And look at the graph. The graph looks like this. On right, it is plus infinite. On left, the values are diverging to minus infinite, like this. Is that okay? This is how you detect oblique and vertical asymptote algebraically without having any graph. There is also a way to detect horizontal asymptote without seeing the graph. In this case, let me do that example and then I will stop. Find horizontal and vertical asymptote of this curve. Okay, first, let's start with horizontal asymptote. How do you detect that? You directly look at the limit of your function as x goes to plus or minus infinite. This is the way to detect horizontal asymptotes for your graph. Okay, normally, okay, degrees are equal. The limit is quickly the ratio of the coefficients, which is 1 in this case, but let me show you how you do that by computing without using any shortcuts like that. So this is 0, this is 0, these are simplified, and the result is 1. Similarly, for x goes to minus infinity, you will have a similar everything is the same above. So 1. This shows you that this verifies for you that y equals 1 is a horizontal asymptote. You see, y equals 1 at around plus infinite and minus infinite, the values of your function is getting closer to 1 for both cases, as the limits are both 1. Okay, this is how you detect horizontal asymptote. Second, vertical asymptote. For this one, you will look at the zeros of the denominator, right? This is 0 if x is minus 2. This is now just a candidate for vertical asymptote. To verify that it is in fact the vertical asymptote, you need to look at the limit of your function as x goes to minus 2 from right and left. Okay, one-sided limits has to be computed. Limits have to be computed for verification of vertical asymptotes. Okay, like that. What are those limits? If you approach minus 2 from right, minus 2 here from right, you are putting kind of minus 1.999 or something. So denominator gets to 0 from positive side. That's why it is plus infinite. And similarly, if you approach from left, this time from this direction, you insert minus 2.0001 kind of points. Plus 2 makes it closer to 0 from negative side. That's why it is minus infinite in this case. You see, this is minus infinite. The values are getting plus infinite. This justifies the fact that x equals minus 2 is a vertical asymptote for this function. And the behavior around vertical asymptote is like this, whether your values gets to minus infinity or gets to plus infinity, okay? So that's it. Any questions about this example now? Any comments? Okay, then I stop sharing my screen. That's all for today. Thank you for your attention.